games. This might be a bit of a shorter talk, we'll see. But this is just as many things I think in this workshop are a bit of a work in progress, and we are still experimenting with a lot of the details of this. So if you have questions about like why did you do this one thing, there are a lot of things we've been trying, so I'll maybe talk a bit about those. Before I get into the work, I just want to talk a little bit about who we are. So I'm from Barnard College in New York. I'm also affiliated with Cross Labs, as is Nicholas, which is an independent research institute in Kyoto, Japan. We are very interested in exploring this concept of open-endedness in general, whether it relates to primarily evolution, but also we have a very strong interest in games and virtual environments. That's why I'm here today. And this is my first games conference I've been to in person, so I'm really happy to meet any and all of you. Just talk to me at some point. It sounds fun. So, why did we do this project? We, like I said, are fundamentally just interested in this idea of open-endedness, and we'll talk about like what that is and why it matters in just a second. But one of the sort of, I guess, main reasons for doing this work is we're very interested in understanding the different kinds of benchmarks that people use for testing AI, and also in particular the ways that they are limited. So a lot of RL domains are sort of like do one thing and do it very well, and we were very interested in understanding are there sort of nonlinear paths that different domains can encompass that might be more challenging for AI to solve. But also, like I mentioned, we're very interested in this concept of open-endedness just as an abstract phenomenon. So we're hoping that this sort of method of analysis can not just apply to games, but can apply to a lot of different kinds of benchmarks and environments. So, okay, what is open-endedness? Why does it matter? So we are thinking in general about this idea of possibility spaces. So possibility spaces can apply to generative systems. We can talk about doing a search through a different kind of space of things that can be discovered, and it's possible that once you get to a certain point, then it opens the door for more kinds of things to be possible. So again, my background is more in evolutionary systems. We do talk about evolutionary innovations in terms of possibility spaces, and we can talk about, for instance, trees allowing giraffes to exist is an example that's been brought up before. So like giraffes couldn't exist if there weren't things for them to eat. So having trees admits the possibility of giraffes. But in video games, we can also talk about, there's a quote from Miyamoto saying that the video game, the possibility space, refers to the myriad configurations the player might construct to see the ways the process experiment system works. So as you explore a game, you find new ways to explore the game, so on and so forth. So we're thinking in the abstract about possibility spaces, and in particular, we're thinking about this idea of something called the adjacent possible. So again, you might have some space that you're exploring, and when you find some states in your possibility space, they open up the remote possible. So things that weren't accessible before become accessible. And if you want a more concrete example of how this happens, we can see in the evolution of technology. So in this case, the printing press came from a bunch of innovations that happened before, but admitted the possibility of new kinds of technologies. So as one last sort of framing for what we're doing, I want to talk a little bit about, again, what is open-endedness and why do we care? And this comes from my home field, which is artificial life, but we're talking about sort of in an abstract what is open-endedness. And this actually relates to Margaret Boden's theory of creativity a bit. So there are a couple different kinds of open-endedness. We can talk about exploratory open-endedness, where you just have some search space and you're searching through it. Very nice. What we're more interested in is this phenomenon of what I'm going to call, and it's not my term, but I'm going to borrow from Tim Taylor and Mark Bordeaux, this idea of door opening states. So you're exploring some space, and then you find, again, these states that once you reach them, they expand your possibility space to either create new instances of the search space that you're already searching, or you can actually expand the dimensionality of your search space in some way by finding these really interesting kinds of door opening states. So what are we doing? We are looking at video games, and we are trying to see if video games have this phenomenon of door opening states. And what we're doing is we're constructing graphs of games from gameplay. So my colleague Nicholas actually sat down and played the game that I'm going to show you in a little bit. And we wanted to see, could we find these states where new things emit new kinds of things as you're playing the game? So we're looking for bottlenecks in this sort of graph that we're going to construct of a game. So one of our other hypotheses is that some of these states are physical, where actually the state of the game means that you, like the way the game is constructed means that you have to do one thing before another. But another part of our exploration is in this idea of cognitive bottlenecks, where a player has to learn a certain skill in order to actually progress through the game. So we're going to look at the topology of the games. And something sort of very related to what we did is this system called MAPI that also constructed topologies of games from RAM, which is what we're going to do. So this was more for the purpose, not of looking at these sort of cognitive bottlenecks and physical bottlenecks, but just for the purpose of automatically constructing game maps and seeing what you can get to from one part of the game to another. So what we did is we found a game called Blobquest. We basically used Blobquest because we wanted to study NES ROMs, and this one is open source, which is nice because we are partially based in Japan and wanted to avoid any copyright issues. So we contacted the author, and he was very happy to have somebody working on Blobquest. So what we're doing is, again, Nicholas played through the game, we recorded the RAM states, and then the methods I'll talk about in a moment were used to identify these sort of bottlenecks or door opening states. And I don't think I can actually show this, but the way Blobquest works is you are basically a blob. It's a platformer game. It's kind of a Metroidvania. So you are going to have this blob that just goes down different parts of the level, collects power-ups that give you different skills. Once you get the different power-ups and the different skills, you're able to get to different parts of the level that you weren't able to get to before. So again, this is sort of like very relevant for this purpose of looking at door opening states that allow different parts of the game that weren't accessible before to become accessible. So we have two methods for looking at what we're going to call physical bottlenecks. Again, this is just how do different actual physical states of the game correspond to another. So what we did, and so if you have questions about sort of how this works, I'm unfortunately going to ask you to go look at the code or email us after. But what we did was looked at the RAM of the game. So the RAM contains a lot of different variables about the game state that are not necessarily accessible by just doing a visual analysis of the games. We tried that initially, but ran into some weird issues with. We actually did try this on some NES ROMs that exist, and we found issues with, for instance, in Zelda and things. If you pulled down a menu, like the algorithm would just spam, like pulling down the menu to get a visual change. So looking at RAM is a better way to see what's going on in the game. So to this, one hot encode each of the nibbles of the RAM, remove the lowest entry values to get a bunch of features, and do k-means clustering to get the nodes in our graph, and then that I'm going to show you next. And then we have links between the nodes that are formed by actually seeing which nodes led to one another when we were actually doing the playthrough. So we get graphs that look kind of like this with this method, which is cool. So this will actually show you a little bit of what Blobquest looks like. So we have our starting position down at the bottom. The green thing is the blob that you play as. And as you can see, there's a bit of a mess going on with the graph. But what we have is a lot of these bidirectional links between graphs where you can see there's a lot of like back and forth where you had to go to a room and then like go to another room right after or something like that. But these are the kind of graphs we get with this method. We have a second method that actually reveals a little bit more of the topology of the game, and this involved taking a neural network and ignore the bottom part of the graph for now, or just look at the embedding. We use a neural network that actually takes as input pairs of RAM states that occur throughout the playthrough, and we again do k-means clustering on the output of that graph. And we can see a different kind of structure, which is kind of interesting. What you can't see, like the inside of each of these nodes is just a number that corresponds to a different state in the graph. But what's important is that we see these sort of loops and cycles and longer trajectories that a player would take in playing this game, where they would be going through longer parts of the levels before coming back to where they were. So we had a couple of hypotheses about what sort of the structure might mean. So short cycles might correspond to quick instances of backtracking, but it's possible, again, that you might have like an enemy moving back and forth on the screen or something like that, and that would actually cause a difference in the RAM state that would lead to these small cycles. But the longer cycles are what we're more interested in, these longer paths that don't involve much backtracking, which shows that the player is actually going through the game. What we're really interested in are these nodes with high degree that might correspond to hubs in the game, where once the player basically comes back with a certain power-up, that again opens the door to getting to new parts of the game. And then the second part of what we were doing was looking at what we're going to call cognitive bottlenecks. So that's the bottom part of this graphic right here. So we trained a world model to predict what RAM states follow attained RAM states. And what this we think corresponds to is, again, how a player would have to learn new skills in order to actually get to the next part of the game. So what we did is we took the graphs that we made in following our first methods and sort of said, well, can we predict what RAM states follow, what previous RAM states. And what we think we see here is that these black links are links that are correctly predicted. The blue links we think show generalization because they are correctly predicted, but they're not connected to an accessible state in the graph. So we can see what would happen without actually having it happen first. And then if you like these graphs, here's a fun graph showing the same thing on our second method. This actually happened really fast, which was surprising. So what that means to us is that once the player learned to solve like the first part of the level, then they knew how to play the entire game. So kind of last things to take away from this. Again, this is very work in progress. We have gone through a lot of iterations of doing this work, and it's extremely sensitive to the architecture choice, to the parameter choice. This is just something we've been playing with for a bit. We would like to remove human play. We did a bit of experimenting with using like MCTS to play the NES games, and that worked for other games, but not for Blobquest, possibly due to the amount of backtracking that you need to do. Again, we didn't report these results, but this does actually work with most NES games if you don't care about the legality of the research you're doing. So that's kind of fun. But we would be very interested in working with somebody who's more of a graph theorist to sort of try to identify what are the actual door opening states in the game a little bit more quantifiably. And we've also been doing some experiments with applying this to not games, but other benchmarks, like using like CFAR and things like that, and we've got some interesting results. So that's that. Again, happy to answer questions, but if you have questions about like, why did we make a certain architecture choice, we've made like a million architecture choices, so I probably can't answer that one, but anything else, we're here.